Now return to maximizing the log likelihood function, L of beta. Recall that L of beta is given by this. Note that L of beta is a real valued function of beta, where beta is given by beta 0 through beta p. Okay, so L of beta is a real value function of beta. So L is a function from Rp plus 1 to R. Further, L is twice continuously differentiable, so we can apply the multivariate Newton-Raphson method. Okay, first, pick an initial value, beta 0, given by A0, A1 through AP. 2, let beta t plus 1 be beta t minus h inverse times the gradient of L evaluated at beta t, where h is the Hessian of L, evaluated at beta t. 3, L attains a max at the beta value to which the sequence, beta 0, beta 1, etc., converges. To apply the Newton-Raphson method, we need to find the gradient of L and the Hessian of L. Recall that L of beta is given by this. So the gradient of L is given by the vector of partial derivatives of L. We also denote the gradient by this. Okay, so we need to know what the partial derivatives of L are. Okay, so the partial derivative of L with respect to beta j is the derivative of L of beta, which is this, and that's a sum, so we take the partial derivative of the sum, which is the sum of the partial derivatives. Okay, so we get this. Now take the partial derivative of this part, we get zij. Take the derivative of this, so we get 1 over all of that times the derivative of the stuff inside, which is this. Okay, now we have a zij here and here, so pull that out. And rewrite this part as P of Zi. Okay, so the gradient of L is given by this vector. We have the partial derivative of L with respect to beta 0. Here, the partial derivative of L with respect to beta 1, and so on. Okay, now we can pull out that summation sign, and we have the sum of these vectors here. Okay, notice that there's yi minus p of zi in every entry here. We can pull that out, and we get this. Okay, notice this here is just zi prime, so we can rewrite it like that. Thus, the gradient of L is given by this sum here. Now for the Hessian, H, it's equal to the matrix where the tjth entry, A sub tj, is given by this. The partial derivative of L with respect to beta j, then the partial derivative of that with respect to beta t. From earlier, we know that the partial derivative of L with respect to beta j is given by this. So the partial derivative with respect to beta t of that is given by the partial derivative with respect to beta t of that sum. Okay, and this is equal to the sum of the partial derivatives of the stuff inside. Okay, here we have a quotient, so we use the quotient rule to get this. Low d high minus high d low, all over low squared. So we get this 1 plus e to the beta transpose zi prime times the derivative of this, which is this, minus the numerator times the derivative of the denominator, which is this, all over the denominator squared. Okay, multiply this out here, distribute to each term here, and we get some cancellation. So we get this here. Notice that we have 1 plus e to the beta transpose zi prime squared here in the denominator. Let's break that apart into two pieces. Okay, so we pull out 1 over 1 plus e to the beta transpose zi prime like this. Okay, so here we have zit. Let's bring that in front here. Rewrite this part as p of zi and this part as 1 minus p of zi. So the partial with respect to beta t of the partial with respect to beta j of L of beta is given by this. Okay, remember this is the tjth term of the Hessian. So the Hessian is given by this. Okay, zi, we have here zi prime times zi prime transpose, and that's going to give us a matrix. We can express the gradient and the Hessian in matrix notation as follows. Let y be y1 through yn. Let z be this matrix here, where the rows of z consist of the zi's. Okay. Let p be p of z1 through p of zn, and let w be this matrix, a diagonal matrix with p of z1, 1 minus p of z1, dot dot dot, p of zn, 1 minus p of zn along the diagonal. Then the gradient of L is given by this, and that's just equal to z transpose times y minus p. The Hessian, is given by this formula, and we can rewrite that as negative Z transpose WZ. So in the Newton-Raphson method, beta of t plus 1 is equal to beta of t minus H inverse times the gradient of L evaluated at beta t, where H is the Hessian, evaluated at beta t. Okay, so we can rewrite this as what we have here, because H is given by this, and the gradient of L is given by this. Okay, where we substitute beta equals to beta t in P and W. Okay, so this simplifies to this, pulling the negative sign out. And here we have beta t. We can rewrite that part as this. So we just added the inverse of Z transpose WZ multiplied by itself here. So that doesn't make a difference. Okay, now here we added W inverse, and that doesn't make a difference since that's just the identity. Also, here we regroup this part, so we have Z beta t here. It's the same thing. Okay, now we regrouped this part here, so we have W inverse times Y minus P. Since we have Z transpose WZ inverse times Z transpose W here and here, pull that out to get this. So that times Z beta t plus W inverse Y minus P. Okay, and we can rewrite this part as all that stuff times V, where V is the stuff inside these brackets. Okay, V is equal to Z beta t plus W inverse Y minus P. So we can write the iterative step in the Newton-Raphson method as beta t plus 1 equals to this, where V is equal to Z beta t plus W inverse Y minus P. This method is then called iterative reweighted least squares. At each iteration, beta t gets updated, and so do P, W, and V.